Hi, in this lecture we're going to be talking about point clouds and their properties. Specifically, we will touch such properties as invariance and equivariance, which are commonly considered when we're learning with point clouds. Next, we will consider how can one construct a neural network on point clouds, and how can one actually build invariances into point cloud-based networks. As an example architecture, we are going to consider the PointNet architecture. We will also further consider distances on point sets, because these are important when we're building computational models such as generative models or autoencoders on point sets. Let's start by comparing depth images that are a familiar data modality to a point cloud. As you remember, depth images are 3D representations of objects using 2D projections, where each pixel in the projected image records distance to a particular point in the scene. To this end, depth images are 2D pixel grids that can be viewed as functions mapping from a 2D domain to a space of signals. In contrast, point clouds are obtained in 3D as XYZ measurements directly by either laser scanning using devices such as time-of-flight cameras and LiDAR, or by combining multiple depth images using a registration process, be it manual or automated. In a sense, the depth image represents one of the three coordinates in the point cloud as a function of the two remaining coordinates, which allows for a simple relation between the two data types. More specifically, if one has access to the intrinsic camera parameters k, the relation between the point cloud p and the pixel image I can be summarized as unrasterization, that is, constructing image coordinates from pixel coordinates, followed by reprojection to 3D space. The properties of the input point cloud are an important factor in understanding the behavior of reconstruction methods. Let us consider some of the properties that have the most impact on reconstruction algorithms. The distribution of the points sampling the surface is referred to as sampling density. Sampling density is important in surface reconstruction for defining a neighborhood, a set of points close to a given point which captures the local geometry of the surface, such as its tangent plane. 3D scans typically produce a non-uniform sampling on the surface, where the sampling density spatially varies. Points that are randomly distributed near the surface are traditionally considered to be noise. The specific distribution is commonly a function of scanning artifacts such as sensor noise, depth quantization, and distance or orientation of the surface in relation to the scanner. Points far from the surface are classified as outliers. Outliers are commonly due to structural artifacts in the acquisition process. In some instances, outliers are randomly distributed in the volume, where their density is smaller than the density of the points that sample the surface. The imperfect registration of range scans results in misalignment. Misalignment tends to occur for a registration algorithm when the initial configuration of a set of range scans is far from the optimal alignment. For instance, in slum-based RGBD mapping, drift can occur, which is the gradual accumulation of misregistration errors between sequential scans taken at very different times, a phenomenon known as loop closure. A motivating factor behind many reconstruction methods is dealing with missing data. Missing data is due to such factors as limited sensor range, high light absorption, and occlusions in the scanning process, where large portions of the shape are not sampled. Before describing the specific properties of the 3D point sets, let us recap several notions important for learning. We will start with a simple example. When detecting cars in aerial images, the object's absolute orientation is not a discriminant feature. If we're confronted with a classification setting, in which we are only interested in the presence or absence of cars in the whole scene, the classification score should remain the same, no matter the absolute orientation of the input scene. If the orientation of the image is changed, such as when following a different flight path, we would expect the car segmentation masks to produce the exact same score over the same cars, but in their new position on the rotated image. More generally, we would like for output to change as the function of the rotation of the input with some predefined behavior. For instance, we might want to retrieve the absolute orientation of cars as a floating point rotation angle. The first case presents the problem as rotation invariant. In the second case, we say that the problem is rotation equivariant. Lastly, we may view the problem as rotation covariant. Let us see how we can define these notions mathematically. Let us start with invariance. Let f be a function implementing a particular mapping from an input space x to a space of outputs y. Let t be a transformation acting in the input space, such as the translation or rotation of the input. We will consider more elaborate transformations later. F is said to be invariant with respect to a transformation t if the following relation holds for all members of the input space x. Specifically, f of t of x should be equal to f of x. Invariance is commonly wanted in classification tasks, such as invariance to rotations, as mentioned previously. Equivariance is the property of a function to commute with the actions of a specific symmetry group acting on its domain and codomain. Formally given two transformations dx and dy acting on the input space x and the output space y respectively, a function f mapping x to y is said to be equivariant if the value produced by the function acting on the transformed input transforms accordingly. A special case of equivariance is invariance, for which dy is an identity mapping. In many machine learning tasks, a set of transformation is known a priori, under which the prediction should transform in an equivariant way. Including such knowledge directly into the model can greatly facilitate learning by freeing up model capacity for other factors of variation. Let us see how these properties apply to the real-world 3D point clouds. Unlike pixel arrays in images or voxel arrays in volumetric grids, point cloud is a set of points without specific order. In other words, a network that consumes point sets needs to be able to accept points in any possible order. The points are from a space with a distance metric. It means that points are not isolated, and neighboring points form a meaningful subset. Therefore, the model needs to be able to capture local structures from nearby points and the combinatorial interactions among local structures. Invariance under transformations means that as a geometric object, the learned representation of the point set should be insensitive to certain transformations. For example, rotating and translating points altogether should not modify the global point category, nor the segmentation of the points. Let us consider a function f that maps the domain x to a codomain y. If f is a set function, meaning that its inputs are sets, then the input domain is instead a power set 2 to the power of x. A permutation is any one-to-one function that reorders elements of the set, for example by permuting natural numbers that index the set's elements. Permutation invariance is a property of a function f to be insensitive to the order of input elements. Since for a set with m elements there exist m factorial permutations, for the function f to be permutation invariant on that set, it has to be invariant to m factorial permutations of the input set in data feeding order. Point-based deep learning architectures are motivated by a challenge to design a neural network for unordered sets. For instance, we might want to use a 2D array to represent a point cloud, where each point is a d-dimensional vector. In simplest case, a point is represented by only xyz coordinates, but it can also include RGB, or laser intensity, or surface normals, etc. Since point cloud is a set, its elements are unordered. It means that with permutation of the new array, it will represent exactly the same set. Therefore, any neural network that is going to operate on sets needs to be invariant to n factorial permutations of the input set. To mathematically formulate the requirements that a function f must satisfy to be permutation invariant, let us consider the following theorem describing the simplest case. A function f operating on a countable set x is invariant to the permutation of instances in x if and only if it can be decomposed in the form where each element from the input set is first transformed using the same mapping phi, and contributions of individual elements are aggregated thereafter with a mapping rho. This theorem has been formulated by the Deep Sets paper and lays the foundation for building set-based neural networks, including neural networks that operate on unstructured point sets. However, we should also pay attention to geometric structure of point sets. From the last lecture, you remember that common transformations that are experienced by objects in R3 are 3D rotations and translations. A 3D rotation is typically defined by a 3x3 orthogonal matrix belonging to a special orthogonal group, that is, it's basically orthogonal, meaning that R transpose R equals 1, and is also belonging to the special orthogonal group, meaning that the determinant is +1. The 3D translation is also a group of transformations mapping Euclidean space to itself that is defined by 3x1 column vector T. A rigid body motion in homogeneous coordinates can be represented by matrix multiplication plus translation. It is also commonly referred to as special Euclidean group, as E3. We commonly want to be invariant to rotations R or rototranslations G. To recap, point sets in R3 is an unordered data modality that must be treated in any particular order, so the functions that we construct that operate on such modality should be invariant under permutations. We should also be invariant under rototranslations, that is, transformations from the special Euclidean group in R3, such as the rigid body motion. Neural networks that operate on point set should utilize somehow a local surface geometry of 3D point clouds, meaning that the neighboring points actually do form a meaningful neighborhood. Let us see how we can actually construct point-based neural networks and how can we inject these invariance properties into these neural networks. The main question with point-based nets is, can we achieve an effective feature learning directly on point clouds? The answer is yes. Point nets perform end-to-end learning for scattered and orderless point data using a unified architecture for various 3D tasks, including object classification, part segmentation, and semantic parsing. Let us start with constructing models that are invariant to n factorial permutations. Mathematically, a neural network is just a function. In a functional view, a permutation-invariant neural network corresponds to a symmetric function. In symmetric functions, for any ordering of the arguments, the function value is always the same. Many functions are symmetric. Two obvious examples are max operation, that is symmetric, and summation, that is also symmetric. Then the question becomes, how can we construct a family of symmetric functions by neural networks? The construction of point nets is inspired by such observation. Suppose f can be written as the following compositional form. Then f is symmetric as long as g is symmetric. From the previous section, this function f satisfies the requirements from the deep sets theorem, and hence can represent permutation-invariant mappings. Guided by this observation, we can construct a neural network based on the symmetric function. Assuming for simplicity that the input point cloud is just xyz coordinates of points, first, we can transform each point independently and identically by a small network H. Or you can think the network will project raw points into a high-dimensional embedding space, or rather expand the dimensionality of each point, not touching the remaining points. This pointwise feature expansion is the first basic operation employed in point nets. Then we can aggregate point embeddings by a simple symmetric function g. Lastly, we post-transform the aggregated information by another network, gamma. This architecture has been dubbed PointNet Vanilla and lays the foundation of the many sibling architectures for point cloud-based learning. A network in this structure is guaranteed to be invariant to the input order, but one question still remains. Namely, among the space of all symmetric functions, what functions can be constructed by PointNet? Interestingly, we can show that any symmetric function that is continuous can be arbitrarily approximated by PointNet. More specifically, any Hausdorff continuous function on sets can be approximated with arbitrary precision when the number of neurons is sufficiently high. You may see that this function f can be seen to satisfy the requirements from the deep sets theorem from the previous section. Of course, higher accuracy requires more internal neurons, but anyway, this is still a very good news. Empirically, we can use multilayer perceptron network for functions h and gamma, which is just the fully connected layers with rectified linear units and batch normalizations. Note that function h is shared across all points, meaning that it has basically shared weights that all update simultaneously when we are training the network. We can further use max pooling, average pooling, or weighted average pooling as symmetric functions g. However, this choice is subject to specific experiments. The PointNet paper was released in 2015 and has since motivated a series of extensions. Today, the literature presents many more new approaches to extract contextual features from local neighborhood in a point cloud. Some approaches such as PointNet++, ggCNN, or PointWeb focus on local structures in the point cloud, where they are able to leverage the local surface geometry of the sampled surface, which is not observed directly. Other methods such as KP-conv or pointwise CNNs convert the completely structureless point set representation into a regular one, using some form of function interpolation, and leverage everyday computational kernels defined on a normal data structure such as the 3D volumetric grid. Many implementations of the PointNet-derived approaches are available in PyTorch geometric library, which is an extension to PyTorch. Next, based on PointNet vanilla, we will study how one can design architectures to make our network more robust to input geometric transformations. As you remember, by these transformations we mean rotations in 3D and translations in 3D, which sum up to a rigid transformation in SE3. The semantic labeling of a point cloud has to be invariant if the point cloud undergoes such geometric transformations. We therefore expect that the learned representation by our PointNet is invariant to these transformations. A natural solution would be to align all input sets into a particular canonical space before feature extraction. This alignment is achieved by applying an affine transformation to input points coordinates. The transformation is predicted by a mini PointNet, which is end-to-end trained with the rest of the network. The mini network itself resembles the big network and is composed by basic modules of independent pointwise feature extraction, max pooling, and fully connected layers. This in spirit is similar to spatial transformer network in images. However, what is different is that for point cloud, a geometric transformation is just matrix multiplication. Therefore, it is very simple and efficient. Compared to image or volume, there is no need for bilinear or trilinear sampling. Similarly, we can use such transforming networks to align points in embedding space. For example, this figure shows a transformation for intermediate embeddings in a 64-dimensional space. To avoid falling into bad local minima, a regularization penalty is added to constrain the transformation matrix to be close to an orthogonal one. To sum up this section, permutation invariance is or can be achieved if we use mappings of the form where each point is transformed by the same function h independently, and then a symmetric function is applied on top of the extracted features. To achieve rotation invariance, we align to a local coordinate orientation by using a learned transformation during training. Recently, baking invariances into point-based and graph-based neural networks has led to progress in obtaining architectures that are at least partially invariant or equivariant to rotations and translations. For example, SE3 transformers present the self-attention model for 3D point clouds and graphs, which is equivariant under continuous 3D roto translations. Tensor field nets are locally equivariant to 3D rotations, translations, and permutations of points at every layer. Quaternion equivariant nets introduce the 3D capsule model for processing point clouds that is equivariant to 3D rotations and translations, as well as invariant to permutations of the input points. Please check out these publications if you're interested. The videos and GitHub links are clickable in the PDF version of the slides. Let us see how transformer networks can be combined to build a final point net architecture for classification. At the very beginning, we have a point cloud with endpoints of XYZ coordinates. The input point is firstly transformed by an input transformer network. Then each point is embedded by a multi-layer perceptron into 64-dimensional embedding space. Then another feature transform is applied. Each point is again transformed in another embedding space, which is 1024-dimensional. Then a max pooling will aggregate all points in a high-dimensional embedding space to output a global feature vector. The global feature vector is finally updated to output class scores for K candidate categories for classification. So far, we have introduced a PointNet classification network. To extend this architecture to segmentation, we need to predict class scores for each point. A simple but effective way to do this is to concatenate local embeddings and global feature vectors for each point. So for each point, we can concatenate the learned local embedding with the global feature vector and use that for parent classification, and finally output M scores for each point to do the segmentation. Let us further understand how we can apply neural networks, such as PointNet, in point cloud analysis tasks. As usual, one of the basic tasks with learning with point clouds is shape classification, where the goal is to accept a point cloud and to predict one of the classes that it might belong to. To basically obtain the synthetic point cloud for training the neural networks, one typically samples the 3D CAD models of everyday objects using sampling techniques such as Poisson disk sampling. Recently, large annotated 3D CAD model collections have been made available, such as ModelNet and ShapeNet collections containing hundreds of thousands or even millions of 3D CAD models. For object classification using point clouds, let us observe that results that one is able to get by training and evaluating on ModelNet 40 shape classification dataset using a PointNet architecture are actually superior to the one obtained previously. In this case, surfaces of each shape were sampled by 1024 points. PointNet, which is the first architecture developed specifically for point clouds, is already achieving better or on par results with several well-engineered 3D CNN architectures. With the emergence of novel technologies such as mobile robotics, many people are seeking more fine-grained shape understanding. For instance, one could seek semantic shape understanding on a sub-object level, that is, semantic part understanding. To this end, one of the most advanced evaluation datasets today is PartNet, offering 3 benchmarking tasks for evaluating 3D part recognition: fine-grained semantic segmentation, hierarchical semantic segmentation, and instance segmentation. Each of the tasks may be performed on an input point cloud. Some results of object part segmentation using PointNet for ShapeNet part dataset for both partial input and complete input. PointNets have also surpassed the previous state-of-the-art using traditional features and also a baseline using 3D CNN on part segmentation. In scene labeling, the goal is very similar to the semantic part segmentation, semantically understanding the role of each point in the scan. However, what distinguishes the two is the scale at which the methods are applied. While object-level segmentation attempts to segment parts of limited objects, scene labeling deals with potentially very large scenes such as rooms or even entire floors or buildings, consisting of billions of sampled points. In this slide, the first row is a rendered view of 3D point cloud, and the second line is segmentation results using PointNet in the same viewpoint. The network is able to clearly segment different semantic regions like walls, tables, chairs, ceilings, etc. As we have seen previously, one of the major challenges with real-world data is that their geometric properties such as presence of noise and outliers, as well as non-uniform sampling, make them remarkably challenging to process. Thus, besides nice performance in 3D recognition, it makes sense to assess how robust is PointNet to data corruption. To do this, one can, for instance, train the model using 1024 points but randomly drop a fraction of points at test time and see how classification accuracy suffers. That would correspond to testing against non-uniform sampling. For PointNet, even after dropping 50% of the points, accuracy drops by only 2%. Another robustness test is dealing with outlier points by allowing the network to see those during training. The net has more than 80% accuracy even when 20% of the points are outliers. The last test assesses how classification performance degrades as long as Gaussian noise is added to point coordinates. Compared with the baseline 3D CNN, PointNet is much more robust in dealing with missing points. In this benchmark, both PointNet and 3D CNN really haven't seen any incomplete data during training time. One question then arises: how can one study why is PointNet so robust to missing data? To answer this question, let's firstly visualize what has been learned by the network as a global feature. For input point cloud, we want to find out a set of points in the input that contribute to the global feature. Notice that some of the points won't be included and won't contribute because of the max pooling operation that we use. Contributing points are denoted the critical point set in the middle row. If we visualize the critical points for the 4 sampled objects shown here, we can see that critical points are capturing contours and skeletons. These are the points that during classification using point nets give maximum activations inside the network. Furthermore, we can find other points in space that won't affect the global feature. As one might guess, most points in 3D space won't affect the global feature, meaning that these points are not limited to the input set. The upper bound shapes illustrate the largest possible point cloud that give the same global feature f of s as the input point cloud s. The upper bound shapes is constructed by forwarding all the points in the edge length 2 cube through the network and selecting points P where point function varies no larger than the global shape descriptor. By definition, any points that fall between critical point set and upper bound set will result in the same global feature vector. Critical set and upper bound set reflect the robustness of PointNet, meaning that losing some non-critical points does not change the global shaped signature f of s at all. In tasks such as point cloud reconstruction, one needs to predict a complete point cloud of a 3D shape from a noisy or incomplete point cloud of the shape object, or from a different representation altogether. One of the challenges in such tasks is how to measure loss during training, as the same geometry may admit different point cloud representations at the same degree of approximation. Along with the usual L2 type losses, what can be used is a solution of a transportation problem based on the Earth mover's distance, or EMD, effectively solving an assignment problem. But first, let us consider the problem of measuring the similarities or distance between two finite sets of points in a metric space. This problem has applications in more than just machine learning, for instance in computational geometry or even philosophy of science. Let us first start with reviewing what is a metric on a non-empty set. A function d that maps two elements into a non-negative number is a metric on a non-empty set X if for any x, y, and z, first, it is equal to 0 only if the two elements coincide. Second, the function is symmetric, meaning that it takes the same value if we swap the two arguments. And third, a triangle inequality holds, meaning that the distance from x to z is does not exceed basically the distance from x to some intermediate point y plus the distance from y to z. Note that for a function to be a meaningful distance function, only 1 and 2 must be satisfied. Let's now consider the following question. How can a distance function on x be extended to a distance function or a metric on the collection of all non-empty subsets of x? Let's start with defining a distance from an element x from a set x to a set y. Let us define it as a distance between the point x and its projection onto y. That is the closest element to x that is available in y, in terms of the original distance function. If we seek to define a distance measure between two sets, x and y, one obvious choice would be the Hausdorff measure, which is simple and trivially computable, but is not very attractive for some applications. The Hausdorff measure defines distances between sets x and y as the maximum of the two quantities, the maximal distance between x and y taken over x, and the maximum distances between set x and the point y over this second set y capital. It does not take into account the overall structure of the point sets and is very sensitive to extreme points in the sets x and y, because it is relying on the supremum. Nevertheless, the Hausdorff distance is a metric if d of x and y is a metric. Let us further assume that d of x and y is a given metric. Commonly, many differences between sets may be expressed by defining a correspondence from elements of x to the elements of y. For instance, one such correspondence may map an element x from the set x to its closest point in the set y. If we do find such a correspondence, the distance measure on sets can take the general form specified by picking an appropriate aggregation operators over sets x and y and a function gamma. Specifically, we first find pairs of points x and phi of x, y and phi of y, using the correspondence function. Next, we aggregate using the aggregation operators over sets x and y separately. Lastly, we employ the gamma function to merge the two resulting values. One example is the Hausdorff distance, where we chose gamma to be max and aggregation to be supremum operators. Let us review a few examples of commonly employed metrics. To plug in a neural network, a suitable distance must satisfy at least three conditions. It must be differentiable with respect to point locations. It must be efficient to compute, as data will be forwarded and backpropagated many times. And third, it must be robust against small number of outlier points in the sets. For instance, a Hausdorff distance will not be robust to a small number of outliers due to the supremum aggregation employed. Let us consider a practical example. On the slide, you were given 2D point sets x and y. How could we possibly measure their discrepancy? So the key challenge would be to determine which point in the x set corresponds to which point in the y set. Let us consider two mappings. Phi of x, which maps a point x to its nearest neighbor in y, and phi of y, which maps a point in y to its nearest neighbor in x. Note that the mappings are general, meaning no one-to-one or any other symmetry correspondence between the two sets exists. The chamfer distance is obtained by choosing the aggregation operator to be a sum and considering a symmetric case. For each point, the algorithm of chamfer distance finds the nearest neighbor in the other set and sums the squared distances up. In the strict sense, the chamfer is not a metric, because triangle inequality doesn't hold. We nevertheless can use the term distance to refer to any non-negative function defined on point set pairs. Viewed as a function of point locations in x and y, chamfer distance is continuous and piecewise smooth. The range search for each point is independent and thus trivially parallelizable. Also, spatial data structures like KD tree can be used to accelerate nearest neighbor search. Though simple, chamfer distance produces reasonable high-quality results in practice. Another distance function commonly used in practice relies on the assumption that the two sets x and y have the same number of elements. The Earth mover's distance relies on building a bijective mapping, phi of x, which maps points to x to its unique counterpart in y and is an invertible one-to-one correspondence between the sets. The EMD distance solves an optimization problem, namely the assignment problem. For all but a zero-measure subset of point-set pairs, the optimal bijection f is unique and invariant under infinitesimal movement of the points. Thus, EMD is differentiable almost everywhere. In practice, exact computation of EMD is too expensive for deep learning, even on graphics hardware. Therefore, an approximation scheme is usually implemented in practice. We can allocate fixed amount of time for each instance and incrementally adjust allowable error ratio to ensure termination. For typical inputs, the algorithm gives highly accurate results with an approximation error on the magnitude of 1%. The algorithm is also easily parallelizable on a GPU. Let's wrap up. So chamfer distances and Earth mover's distances are simple functions of coordinates, and they're differentiable almost everywhere, and the correspondence is unique in general positions. With infinitesimal movement, the correspondences do not change, and so these distances can be effectively employed in point set generation tasks.